Welcome to Tellabs Optical LAN Traffic Management. This video is designed to help prepare Tellabs partners' sales teams to be able to reference and position optical LAN solutions to their customers. Specifically, this module will deal with the positioning of Tellabs Optical LAN Traffic Management. The topics covered in this video will be modern traffic patterns, common traffic restrictions, LAN performance, and managing bandwidth. The days of building local area networks to support telephones, desktop workstations, and local switch traffic have passed. 10 years ago, LANs were designed to support peer-to-peer traffic flows because 80% of the traffic stayed local. But today it is expected that 90% of LAN traffic flows directly to the wide area network. The modern high-performance corporate LAN needs to support new smart building systems, a wide range of mobile devices, cloud computing, and a constant influx of new software applications. IT professionals also find themselves balancing corporate data, employee personal data, external malicious attacks, and internal security vulnerabilities. With changes in the workplace come changes in LAN traffic management, which trigger a corresponding change in the LAN infrastructure architecture. Copper-based LANs were once adequate for telephones and desktop workstations, but their architecture is cumbersome, less secure, inefficient, and expensive. One undisputed fact is that fiber provides many benefits over copper cabling. One of the most startling is in the area of bandwidth. It is prudent for IT professionals to investigate common traffic restrictions. These restrictions are found at the connection to the wide area network or internet service provider, the core router, shared resources, split ratios, and oversubscription concentration. Today, the majority of LAN traffic is destined for the WAN or ISP. The question becomes, what size WAN ISP connection has the company purchased? More than likely, the WAN ISP connection capacity is measured in megabits per second and shared across all users and IP Ethernet endpoints within an enterprise facility. Even if a large corporation has purchased outside connectivity measured in gigabits per second, it is highly unlikely that internal math would prove that all user and IP Ethernet endpoints are receiving gigabit rate data speeds. For a 1,000 user endpoint enterprise corporation example, a 48-port gigabit Ethernet workgroup switch would need to be only equipped with 40 user endpoint connections and be uplinked to 4 10 gigabit per second interfaces. The core router would then need the density to aggregate 100 10 gigabit per second interfaces traveling back from 25 48-port gigabit Ethernet workgroup switches. Ultimately, the core router would need to have a terabyte connection to the WAN ISP. Such a scenario would be very expensive, at best 99.9% availability with zero redundancy resiliencies, and thus highly unlikely to exist in the real world. The core router in the building's main data center is the focal point of the LAN's traffic. It provides connectivity to WAN, ISP, external VPNs, all content, and all corporate resources. This location in the network requires the highest degree of attention to ensure that no traffic bottlenecks exist and no security breaches occur. The core router is a sophisticated piece of equipment and an expensive one. Since optical LAN has the superior aggregation and distribution, by deploying optical LAN, you can save ports on the core router, thus saving money on the core router and saving money on your total LAN infrastructure. Ethernet by nature is a shared resource. Passive optical distribution networks are negatively described as shared resources across their passive optical network splitters. However, it is also a fact that everything on a legacy copper-based active Ethernet network is shared beyond the first 100-meter point-to-point cabling drop. Furthermore, ever-popular cloud-based computing technologies are a shared resource as well, and there are good business reasons why shared resources are acceptable. As with cloud-based computing, optical LAN takes advantage of this architecture to simplify the LAN, lower costs, reduce energy consumption, and save space without sacrificing any security. With optical LAN, passive optical distribution splitters are used throughout the distribution, aggregation, and access networks. These splitters commonly are deployed in a 1 to 2, 1 to 4, 1 to 8, 1 to 16, and 1 to 32 increments. Similarly, a legacy copper-based active Ethernet workgroup switch provides a 1 to 24 or 1 to 48 split ratio. That is, these workgroup switches share common uplinks across 24 or 48 ports. At an even more granular level, one would find that 24 or 48 port workgroup switches or 24 or 48 port service module subcomponents are composed of 1 to 4, 1 to 6, and 1 to 8 Ethernet chips that have 1 gigabit per second or 4 gigabits per second traceback to a supervisor engine. All of these embedded splits of legacy copper-based active Ethernet are not exposed to network architects and engineers. Therefore, the benefit of optical LAN optical distribution splitters is that they provide network architects and engineers with the flexibility to match low bandwidth, high density endpoints with high split ratios and high bandwidth, low density endpoints with small split ratios. Whether we are examining WAN ISP connectivity, core router, shared resources, and/or split ratios, oversubscription or concentration exists at many points in the network. And in fact, copper-based LAN design guidelines call for a 20-to-1 oversubscription because it is not generally practical to provide line rate for every port upstream from the access to distribution switch, the distribution to core switch, or even for core-to-core links. The highest levels of oversubscription will occur near the WAN ISP connectivity and core router. What is important for IT professionals is providing traffic management for the best possible network performance by taking advantage of optical LAN's superior security, segmentation, and QoS capabilities. To ensure the highest degree of LAN performance, traffic management needs to balance bursty traffic, interactive traffic, real-time latency-sensitive traffic, and non-real-time traffic. Optical LAN can accomplish the highest LAN performance through traffic segmentation, low latency, and QoS mechanisms while drastically improving network security compared to the legacy copper-based LAN alternative. Legacy copper-based LANs that place all traffic in a single broadcast domain can easily overload the network. The better design is to create a traffic or service segmentation through advanced VLAN capabilities. Optical LAN enables service-level VLANs that segregate and secure data flows to optical network terminal Ethernet ports. VLAN trunking, termination, and translation allow for rate shaping on a per-service type. Traffic classification is accomplished per IEEE 802.1p, IEEE 802.1q, and even DSCP to guarantee voice quality. With VLAN trunking, you can support multiple services and multiple end devices per ONT Ethernet port. Network performance is affected by a large number of factors in addition to bandwidth. Increasing bandwidth capacity does not directly equate to better network performance. Service performance is also directly dictated by latency, jitter, packet loss, and congestion. Optical LAN has proven 1 millisecond latency measured during formal multi-vendor end-to-end interoperability testing at U.S. Department of Defense certification through Joint Interoperability Test Command, or JITC. In 2008, the U.S. Department of Energy brought together more than 60 experts from the energy, telecommunications, and IT industries. The DOE wanted them to brainstorm ways to improve efficiency of, among other things, data centers and telecommunications equipment. One of their findings stated that reducing the number of optical to electrical and electrical to optical conversions resulted in better network performance and lower energy consumption. Optical LAN does exactly that. In fact, optical LAN can eliminate all of the OEO conversions over a 30-kilometer reach. Strict quality of service, or QoS, is delivered through optical LAN via traffic segmentation classification, rate limiting, policing, queue management, scheduling, and shaping mechanisms. As stated, traffic classification is done for all ingress traffic based on traffic type defined by VLAN during provisioning. Rate limiting and policing is defined in the service level agreement by setting committed information rate, excess information rate, and ACL filters. This sets the guaranteed bandwidth per user, per service, or per end device while smoothing bursty traffic and establishing ultimate rate limits. Based on traffic management criteria, The system then employs tail drop or weighted random early discard modes against throttled traffic. At that point, queue management kicks in. Optical LAN supports 8 class queues available within the network and 4 class queues available at each endpoint. This ensures strict traffic delivery based on hard QoS parameters by providing IT professionals with granular traffic shaping capabilities. Consider this chart of common LAN service bandwidth requirements per user. Back in the days when IT professionals did not have the ability to enforce traffic management policies, LANs required relatively big pipes operating at 50% capacity to ensure no collisions. When IT professionals take advantage of traffic management policies of strict service segmentation and hard QoS, you may be surprised at the true real-world bandwidth requirements of the most common LAN services. In 2013, Gartner Research did a study of estimated peak bandwidth per user in a commercial enterprise LAN and found that 200 kilobits per second was more than sufficient. This study took into consideration the impact of video, wireless, and cloud computing on the LAN. Then Gartner Research went on to estimate the future expansion of video, wireless, and cloud computing and offered a forecast of projected peak bandwidth per user. The outcome of the research stated that heavy video, wireless, and cloud computing would require bandwidth per user in a 1 megabit per second to 7 megabit per second range. So guaranteeing 2 meg or 10 meg service rates with the ability to burst to 1 gigabit per second is more than sufficient for today's modern LAN traffic bandwidth. Optical LAN can deliver symmetrical gigabit rate service at an ONT Ethernet port. When and where to allocate gigabit rate service is at the discretion of the network architects and engineers. Based on the previous bandwidth chart, one can see that guaranteeing 10 megabits per second or 100 megabits per second service rates is more than sufficient for most LAN services, including video, wireless, and cloud computing. In fact, while network managers can create global traffic profiles at 10 megabit per second or 100 megabit per second rates and align them with users, ports, and services, the optical LAN transport can always accelerate to gigabit rate speeds as network congestion allows. In this module, you have learned about modern traffic patterns, common traffic restrictions, LAN performance, and managing bandwidth.